Hello and welcome to part 2 of topic 5 on the thermal properties of polymers. Let's talk now specifically about the thermal conductivity in polymers and how that relates to polymer structures. It turns out that thermal conductivity of polymers is proportional to the density of the polymer, the speed of sound through the polymer, and the specific heat, but is also proportional to something called the intermolecular spacing, or L. In other words, the farther the chains are spread apart, the faster the heat can be transferred through the material. In addition, thermal conductivity is influenced tremendously by the crystallinity of the polymer. Amorphous polymers have relatively low thermal conductivity. The reason for this is that the disorder in the structure makes it difficult for phonons, which carry the heat, to transfer from one side of the material to the other. This conductivity increases gradually with temperature, but not in a very dramatic way. On the other hand, semicrystalline polymers have relatively high thermal conductivities at temperatures below the glass transition temperature, and this remains fairly constant until you approach the melting point. At the melting point, the thermal conductivity drops to be equal to that of an amorphous polymer, because now you're in a polymer melt. Conductivity can also be affected by anisotropy. So if we draw a polymer and orient the chains parallel to the drawing direction, we see that the thermal conductivity increases. Again, this is due to the fact that the drawing process creates order within the polymer structure, aligning the chains, which makes it easier for phonons to travel through the material. We see as well that in the perpendicular direction of the drawing process, the thermal conductivity degrades or is decreased. Finally, we see that as we add fillers to the polymer, it tends to increase the thermal conductivity. The glass fillers act as a short circuit path, if you will, for the phonons to travel through the polymer, increasing the thermal conductivity of the material. So here, for a nylon material filled with glass fiber, we see a relatively low thermal conductivity, which then drops off at the melting point and then levels off for the polymer melt. By adding glass fiber, we increase the thermal conductivity of the solid polymer and even increase the conductivity of the polymer melt as well. This is important if we're trying to cast a polymer with glass reinforcement, because we want to have high thermal conductivity of the polymer melt in order to generate rapid cooling of the part. Specific heat is also affected by structure. In this case, we notice that amorphous materials have a fairly constant and low specific heat. But if a material is semicrystalline, it illustrates a high specific heat right at the melting temperature and then a drop-off. So if I wanted to determine the melting point of a polymer, one way that I could do that would be to increase the specific heat and then increase the temperature and measure this increase in specific heat at the melting temperature. We also see that thermal diffusivity is affected by the polymer structure. So for example, the amorphous materials exhibit a glass transition and a sudden decrease in thermal diffusivity, but then it remains a rather linear response with temperature. Semicrystalline materials also exhibit a glass transition point in the thermal diffusivity, but more importantly, they exhibit a large drop-off in thermal diffusivity at the melting point. This is due to the fact that at melting, the specific heat of semicrystalline materials increases dramatically and the conductivity also decreases. So when you take these two things into account, we get a decrease in the overall thermal diffusivity of the material.